Hi class 12, hope you all are in good health, and starting with this video for you all, I want to do my lessons on this board. I think it will be better than doing it on paper and trying to explain you things there. Now since we don't want to make this video a lengthy one, so therefore let us straight away jump to the topic of the day, which is hysteresis, or rather called a hysteresis loop. Now, at the very beginning, let me tell you that the syllabus specifically mentions that this topic is not to be evaluated, which means I don't think you will get questions from this topic. Alright? So, but still you should have some understanding about it. So, very quickly and very briefly, let me tell you what this is all about. In an external magnetic field, or rather let me say, in an external magnetizing field, capital H, you place a ferromagnetic substance, iron, nickel, cobalt. Okay, what happens is this ferromagnetic substance in the external magnetizing field, it gets magnetized. So to say, magnetism is induced in this substance. Alright, so what hysteresis loop gives us is, it shows us what the journey of magnetization of this ferromagnetic substance will be when the external magnetizing field is changed, is varied. So thereby it is a plot of the intensity of magnetization, capital M, or you could also say the magnetic induction, capital B. You can also plot capital B along the y-axis, but along the x-axis we should have the magnetizing field, capital H. So initially we only have the ferromagnetic substance, the external magnetizing field is 0. So there so to say, the ferromagnetic substance will not act as a magnet. Okay, so it will have, so to say, 0 magnetic properties. Now when I say that, we need to be very, very careful, because ferromagnetic substances, they have, domains in which of course they have a number of dipoles oriented in a certain direction. Don't forget that. Okay, only thing is it is not behaving as a magnet in the absence of an external magnetizing field. So the intensity of magnetization in the absence of the external magnetic field is 0 in the ferromagnetic substance initially. So we go on increasing the external magnetizing field. What happens is the intensity of magnetization also goes on increasing. It also goes on increasing. Okay, so to say, the dipoles in definite domains, they start getting aligned in the same direction. All of the dipoles, they start getting aligned in the same direction. As we go on increasing the value of capital H, more and more dipoles gets aligned in the direction of the magnetic field. So intensity of magnetization starts to increase. Now, you further go on increasing, it reaches saturation. Alright, so since it reaches saturation, there is no point increasing capital H further. So this is the point of saturation. Now what you do is, you then have to start decreasing the value of your capital H. You start decreasing your value of capital H. What is seen is, the intensity of magnetization also then goes on decreasing, yes, but it does not decrease along the same path it had started from. Let me name this point O, and this is point A, the point of saturation. So after it reaches point A, the point of saturation, we start decreasing the external magnetizing field, but it doesn't follow the path AO it had started with. Okay, so what instead happens is, of course, intensity of magnetization starts decreasing with the decreasing the external magnetizing field, but it starts following a different path altogether. So you are decreasing H, the intensity of magnetization M also goes on decreasing, it goes on decreasing, it goes on decreasing. And what is seen is, when you make the external magnetizing field 0, so to say you remove the external magnetizing field completely, what is seen is, this ferromagnetic substance will retain some magnetic behavior. So to say, this ferromagnetic substance starts behaving like a magnet now, although the external magnetizing field is not there. So it has retained some magnetic properties. There is some intensity of magnetization here still. Let me call this point B. This OB, so to say, is called retentivity of the substance. The amount of magnetic behavior the ferromagnetic substance has retained, although the external magnetizing field is removed. This property of the ferromagnetic substance is called retentivity. R-E-T-E-N-T-I-V-I-T-Y, retentivity. The ability to retain magnetic behavior. Then you're not satisfied, because although you remove the external magnetizing field, it has retained magnetic behavior. You're not satisfied with that. You want to completely remove all of the magnetic behavior it has retained. So what you do is, you start making the magnetizing field negative now. So magnetizing field is made negative means what? It means that you have now changed the direction of the external magnetizing field. So the external magnetizing field is in this direction now, towards the left hand side, so to say. So you change the direction of the external magnetizing field, then after it is seen, as you go on increasing the value of external magnetizing field in this direction towards our left hand side, as you go on increasing the value of H in this direction, the external magnetizing, the intensity of magnetization goes on decreasing. It goes on decreasing. And at a certain negative value, you will see that the ferromagnetic substance, the ferromagnetic substance gives away all of its magnetic behavior it had retained. So to say, it is simply acting like a ferromagnetic substance now. Then you further go on increasing H in this direction. Then after, what happens is, this body starts, the ferromagnetic substance starts increasing intensity of magnetization in the opposite direction. The magnetization increasing in this direction. So to say, the dipoles inside the ferromagnetic substance gets aligned in this direction now, in the opposite direction. So it starts increasing M, the intensity of magnetization starts increasing in the opposite direction, and here also it reaches saturation on further increase of capital H. Okay, so it reaches saturation. Then after, again what you do is, you start decreasing the value of H. You slowly, gradually go on decreasing the value of capital H. You will see the value of capital M also goes on decreasing. The value of capital M goes on decreasing. And when you completely remove the external magnetizing field in this direction also, completely remove, then you will see again that the ferromagnetic substance has retained some magnetic behavior because of its retentivity. It has retained this OC, let me call this OC. So it has retained again some magnetic behavior, but it's in the opposite direction to the previous case, mind you. Okay, then again you want to completely remove the magnetic behavior from the ferromagnetic substance. You again go on increasing capital H in this direction. So to say, you are very cruel, so to say, you are being very cruel to the ferromagnetic substance. Alright, you again start increasing your capital H external magnetizing field in the previous direction, that is towards the right hand side. With that increase, the intensity of magnetization goes on decreasing. The intensity of magnetization goes on decreasing, and at a certain value of H, the ferromagnetic substance gives away all of its magnetic behavior. Okay, so here it loses all of its magnetic behavior. Whatever number of dipoles were aligned in the direction of the magnetic field, you lose that. Then you further go on increasing H. I don't know what kind of a person you are. Alright, you are not satisfied with anything. So you go on increasing H in this direction. You go on increasing H. You go on increasing H. The intensity of magnetization also increases and again reaches saturation. Okay, so this curve is what is called a hysteresis tube. So after it reaches saturation, again you decrease H, it is going to follow this path now. A, B, this path, the same path it had followed previously. and you go on decreasing edge. When edge is 0 again, it retains some magnetic behavior. You further go on decreasing the value of edge, or you increase the value of edge in the opposite direction, and goes on decreasing. The ferromagnetic substance loses all of its magnetic behavior. You further increase edge in this direction, then the intensity of magnetization increases in the opposite direction, reaches saturation, and the whole process, you go on changing the direction and intensity of capital H, the magnitude of capital H. This loop, the outside loop, is forever followed, and this loop is what is called a hysteresis loop. But mind you, the ferromagnetic substance will never ever again follow this path AO. Never again follow this path AO. This is the path it starts with, but never ever then it follows. Okay, and like I said, OB or OC for that matter is what is called the retentivity, the ability to retain magnetic field or magnetic behavior, although the external magnetizing field is no longer existing. That is what is called your retentivity. And there's something called coercivity. There's something called coercivity. What is this coercivity? The external force that you need to apply, such that whatever magnetic behavior is retained, all of that magnetic behavior is lost. The force that we need to apply, such that all of the retentivity, so to say, is gone, is what is called your coercivity. Okay, if you have a magnet also, you go on banging that magnet on the floor, okay, you will see eventually the magnet loses all of its magnetic behavior. That is the ability to attract iron or similar substances. Okay, so that is about hysteresis loop. By the way, you will be asked questions like, what kind of a substance do we need to make a permanent magnet? I hope the spelling is correct. Permanent magnet. For a permanent, it's not permanent, yeah, permanent magnet, the kind of substance you need is, it should have high retentivity. Permanent magnets should have high retentivity, of course, okay, it should be able to hold on to its magnetic behavior for a long time, high retentivity. It should also have high coercivity. Coercivity. It should also have a high coercivity. Okay, you need to apply a lot of force such that it gives away all of its magnetic behavior. So that is what a substance used to make a permanent magnet should have. Okay, high coercivity and high retentivity. Likewise, for an electromagnet. For an electromagnet, what kind of a property should the substance used to make an electromagnet have? In order to make electromagnets, we use soft iron. We use soft iron. The iron that we use to build homes also. Okay, build a house. Soft iron. It has low retentivity, because the moment you turn off the current, it should lose all of its magnetic behavior. That is what is required to make an electromagnet. And of course, it should also have a low coercivity. Low coercivity. Low coercivity. Okay, and in a transformer also we use a soft iron core. Okay, because soft iron cores have low retentivity, low coercivity. Also remember, in a transformer what happens is you constantly go on increasing and decreasing and changing the direction of the value of the external magnetizing field in a transformer. So what happens is, in a ferromagnetic substance, you need to understand this carefully. when the ferromagnetic substance is made to undergo this whole process of getting magnetized and losing its magnetic ability, okay, and getting remagnetized again, when it goes through all of this process again and again, it's kind of the ferromagnetic substance gets fed up. Alright, obviously you are made to do one thing and not do it again, do, undo, the whole process going again and again, obviously you get fed up. Alright, so what happens is, because of this process of getting magnetized and demagnetized, magnetized and demagnetized again and again, the ferromagnetic substance gets heated. So to say, there is loss of energy in the form of heat. Okay, when this process of getting magnetized and demagnetized goes on again and again. And that loss of energy in the form of heat is what is called hysteresis loss. That is called, let me erase this part here. It is called hysteresis loss. Hysteresis loss. Loss of energy in the form of heat. In the form of heat. Because of course of this process of getting magnetized and demagnetized again and again, remember. Alright, so in electromagnets we use soft iron because soft iron has low hysteresis loss. Okay, so in a transformer, what is the kind of substance, what are the abilities the substance requires to use in transformer is, it should also have low hysteresis loss. It should also have a low hysteresis loss. Okay, so this is about hysteresis and hysteresis tube, and with this we end the topic magnetism. Remember, in the next class or in the next video we are going to start with electromagnetic induction. Thank you.